This is the video lab report for Physics Lab 1 on constant velocity. In this lab, we will be using Newton's second law of motion to explain and predict the future. Okay, here are some equations that we derive from Newton's second law of motion. On this left side over here, we have the position equation, or the equation used to find position, which is used to predict where the object will be, our system will be. Right here where it says x2 and x1, this is the same equation that we are using in our course, except replace x with 2 for p1 or p initial and p final. On this right side over here, this is our velocity equation. And here imagine v1 and v2. This is the same equation we use. We can imagine this as v initial or v final, or whichever numbers we choose to describe it, or letters. Speaking of our system, this soccer ball right here with a mass of roughly 0.4 kilograms and a size of a little bit more than 15 centimeters, as we can see here with our calibration stick, will be our system. And the forces acting on the system will be from the surroundings, which you can't quite see here, but someone will be kicking the soccer ball. As we kick the soccer ball, we set the ball into motion. And once we set it into motion, it will carry on in a constant motion because no outside forces will be acting on it, theoretically. However, this is the experimental version, which is done in the real world, where we will have some outside forces acting on it, which will not be taken into account when we produce the model. In this case, because it's such a short distance, it's probably safe for us to assume that there will be no significant effect from the surroundings. But let's go ahead and take a look and see if our assumption is correct. Okay, so the ball, starting here at the origin, well, roughly the origin, 0.01001, as close as I was able to get it, travels across in the positive x direction, staying roughly on the y-axis. These red points right here are what we designate as the point of mass, and it produces over here a position by time chart. Here we have our Python code that was written to produce the model and predict the future, as we stated earlier in the video. Here we have ball.m representing our system's mass, which is not in the empirical system, it's in the SI units, so this is in kilograms. Right here we have the ball's initial position, which is the position 0.00100, and the ball's average velocity as taken from the experimental data. And since we're not time travelers, we'll choose to start the clock at t equals 0. And considering that our video is shot at roughly 30 frames per second, we'll have delta t at 1/3 of a second. Right here we have our clip ends after 0.867 seconds, and since there is theoretically no net force, we plug in 0 for the net force vector, and we use the equations that we were previously shown that we derived from Newton's second. So translating this Python code here, we have v final, or v2, equals v1, or v initial, plus f net divided by the ball's mass times delta t. And right here for our position equation, we have the position final, which x2, p2, p final, equals p initial plus the velocity, the final velocity here, times delta t. Okay, let's see what happens when we run this. Alright, here we have our graph that is produced with our model predictions of the future. Okay, so here's the graph that represents the model versus the experiment. Here, the red line represents the model position, which is our predicted motion. Now, as earlier stated in the video, surroundings acting on the system in the experiment could possibly be, say, friction. Now here we can see that was virtually negligible because the line here on this time position graph does not curve, it stays straight, which means it remained at a constant velocity, which is in line with the model position. What if, while we were analyzing the data in Tracker, we would have changed the orientation of the axes? Basically, the answer to that is nothing would have happened in terms of our data as far as information goes. However, it would have most likely just changed the orientation of this graph. It would have changed how this goes up from left to right to probably something more like down from left to right. Now, if the experimental position, or if the experimental position and the model position differed in terms of the ending points but had the same origin, then that would mean that we had a poor choice of average velocity. And all right, thanks for watching.